Welcome to explanation-based weekly supervised learning of visual relations with graph networks by Federico Baldassarre, Kevin Smith, Josephine Sullivan and Hossein Azizpour at KTH Stockholm. A visual relation is a triplet of subject, predicate and object, such as person, eat, apple, where the subject and the object are spatially localized in the image. Visual relationship detection has been tackled with modern computer vision methods, also thanks to large-scale, fully annotated datasets. However, collecting data for fully supervised training is expensive due to combinatorial explosion of object and predicate classes and laborious bounding box annotations. Previous works have demonstrated learning relationship detection from unlocalized triplets. Of course, removing the need for box annotation speeds up data collection, but these methods still rely on exhaustive triplet annotations. In this work, we demonstrate learning visual relationship detection using weak, image-level, predicate-only labels, such as eat or sit on. Notably, the notion of objects and interactions is absent from the raw training data, and it will only arise by applying the right inductive biases and object-oriented explanations. We take inspiration from recent works on weakly supervised learning, where object detection is learned from image-level labels. Broadly speaking, these methods employ a convolutional neural network trained for image classification. In the forward pass, the classifier assigns a label to the input image. Then, an explanation method produces a heat map of the image patches that were most relevant for the prediction. Finally, object detections are derived from the explanation, without requiring strong annotations. In this work, we take this idea one step further by employing graph networks and object-oriented explanations. For the first time, we demonstrate the applicability of this line of work to weakly supervised learning of visual relationship detection. As the first step, we build a predicate classifier that can be trained using the weak image-level annotations available in the dataset. The design choices for such a classifier introduce two important inductive biases that are key for later recovering relationship triplets. First, physical objects in the input image are explicitly represented using a fully connected graph of all instances detected by an object detector. Specifically, we use an off-the-shelf, faster RCNN implementation, which can be trained in advance on a cheaper object detection dataset. Second, the graph network architecture of the predicate classifier is designed to favor pairwise relations between input nodes. This is achieved by using a single layer of graph convolution that updates the features of each edge by aggregating information from the two adjacent nodes. In the output layer, all edges are pooled to produce a single prediction vector for image-level predicates. Once the predicate classifier is trained, relationship triplets are recovered as the object-oriented explanation of its most confident predictions. Each predicate prediction is attributed to one or more pairs of input nodes, which are assumed to represent its subject and object. Specifically, sensitivity analysis is used to carry out the backward explanation from the output prediction to the input nodes, but other gradient-based explanation techniques perform similarly in the experiments. Then, an additional directionality prior disambiguates between semantically opposite triplets, such as person hold plane versus plane hold person. This prior is required as a consequence of the weakly annotated training data that contains no hint about the directionality of relations. Notably, each prediction is attributed to physical objects present in the image rather than to raw pixels, which makes explanations more intuitive to use for relationship detection. To begin with, we apply our method to the visual relationship detection dataset, which contains both actions such as drive and spatial relations such as next to. In all three evaluation setups, our method achieves recall scores that are comparable to other fully and weakly supervised methods. The results for recall at 50 also highlight the effect of the directionality prior on the ranking of relationship triplets. In fact, when using an uninformative prior, we notice that both a correct triplet and its opposite would appear among the top scoring detections. Instead, a simple frequency-based prior immediately doubles recall at 50, by eliminating triplets with a wrong subject-object order, such as car, drive, person. Another dataset included in our experiments is HICO-DET for human-object interactions. The proposed method achieves mean average precision scores that are compatible to fully supervised methods. Detection results can be further improved if the input graph is restricted to having edges from human to object nodes only, which is equivalent to using a strong directionality prior. As a last experiment, we consider the UnRel dataset that is commonly used to evaluate detection of unusual relations. Good performances on UnRel suggest that training with predicate-only annotations improves generalization to rare or unseen triplets. We now show 3 failure cases that originate at different stages of the relationship detection pipeline. In the left image, the object detector misclassified the dog for a person. In the middle, the predicate classifier assigned a higher score to the predicate hold than to the predicate where. On the right, the directionality prior did not recognize the correct order of subject and object. In conclusion, our method is able to learn relationship detection from weak, image-level, predicate-only labels, while remaining competitive to fully and weakly supervised methods. On the one hand, this enabled a faster and cheaper data collection, since a single image search can yield many diverse examples of the same predicate. On the other hand, less specific and less comprehensive annotations seem to improve generalization to rare triplets. More generally, we demonstrate a case for object-oriented explanations as opposed to pixel-wise heatmaps, since the former are more intuitive for humans and more useful for downstream tasks. In regard of future directions, we have highlighted the lack of directionality information in predicate-only labels, which should be addressed through a stronger prior, for example based on language, or through a more principled solution. Furthermore, the proposed explanation-based method has the potential to be applied outside the visual domain, for example, to other applications where structure and relationships are important, such as chemistry and biology. Thanks for your attention.